Hello everyone, how are you doing today? My name is Thomas Neild. In this video, I'm going to show how you can use a tree search algorithm to generate a classroom schedule. You can also apply this to staff scheduling, scheduling server jobs, a lot of discrete optimization problems where you have a set of constraints and limited resources to allocate them. And you can use integer programming, meta-heuristics, or another search technique to pack the right discrete variable values to come up with your desired outcome. So in this case, we're going to just schedule some lectures against some classrooms, or just one classroom in this example. I'll explain how to do multiple later. One of the reasons why I really like this example is because it's something we encounter quite a bit. And this form of AI has been around for a very long time, and yet not many people know about it. So I'm very happy to share it with all of you. So let's go ahead and get started. So you need to generate a schedule for a single classroom with the following classes. So you have Psych 101, English 101, etc. Some require 1 hour when 2 sessions a week. Some require 1.5 hours with 2 sessions a week. So there's different sets of durations and recurrences that each of these classes have. And the available scheduling times are Monday through Friday from 8 a.m. to 11:30 a.m. As well as 1 p.m. to 5 p.m. So there's a lunch break in between. And the slots these classes are scheduled are done in 15-minute increments. So when you schedule Psych 101, it needs to be at 8 a.m., not 8:05 a.m. It has to be 8 a.m., 8:15, 8:30, etc. It does on the quarter of every hour. And one thing we're going to assume is that for every recurrence of a given lecture, so for instance, Psych 101, it requires two sessions a week, they will be recurring at the same time. So if we schedule Psych 101 on Monday at an 8 a.m., the next session has to be on Wednesday at 8 a.m. And we'll assume there's a 1-day gap or a 48-hour gap between the start of each repetition. All right, so one of the very first things you will want to do is you will want to visualize these possible start times of each class as a grid. And on the horizontal axis, you're going to have every single time throughout the planning week. So you can see it starts at Monday at 12 a.m. and then it ends at Sunday, 11:55 p.m. And this column with the dots right here, that is just a placeholder showing that we've collapsed the rest of the week because we don't have enough space to show every single 15-minute interval throughout the week. And on the vertical axis, we have the classes, so Psych 101, English 101, and we're going to set, and the intersection between each time slot and class is going to be a 1 or a 0. A 1 indicates that is the start of the first session of that class. And we will solve for these 1 or 0 variables using a branching algorithm, which I will show later in this video. So before we go into the branching algorithm, let's kind of think about our constraints and how we prevent classes from overlapping on each other. So let's say that our algorithm or our solver, whatever we're using, it schedules it looks at Psych 101 being at 9 a.m. and Sociology 101 being at 9:15 a.m. Now, let's look just at the 9:45 a.m. slot. So notice that 9:45 a.m. slot is occupied twice, and therefore this is not what we want. We want only one class occupying that given slot. For the 9:45 a.m. slot, we only want one class occupying it, but we have two. And how do you mathematically describe this? You can see that Psych 101 and Sociology 101, that it touches the 9:45 a.m. slot, and the slots that affect the 9:45 a.m. slot, the ones that precede it, the sum of those are 2. And so if we move the Sociology 101 to 9:30, it's still double booked on the 9:45. And if we push it to 9:45, it is still double booked. But as soon as the Sociology 101 moves to 10 a.m., everything is good. The sum of affecting slots for that 9:45 a.m. slot, for that 9:45 a.m. block, is 1, whereas the previous cases you saw before, they were 2. So how exactly do we visualize this on a higher level? So essentially what we have to do is for every block, every 15-minute block, we must sum all the affecting slots as shaded below for the 9:45 a.m. And you can identify these affecting slots by the class duration. So for instance, Psych 101 is 1 hour. Therefore, all slots from 9 a.m. to 9:45 a.m. affect the 9:45 a.m. slot being occupied. So the sum of all the values in this blue area, as indicated by the class durations, they must sum to no more than 1. So whenever you have a sum of two or three, etc., in this blue shaded area for the 9:45 a.m. block, then the 9:45 a.m. block is double booked. And we need to do this. Let me go ahead and rewind. We need to do this for every single 15-minute block. We need to come up with a model that does this for every single block. We can also fix blocks to 0 that are outside the operating day. So for instance, 7 a.m. is outside our operating window, and so is midnight. So we just block those to 0. And any affecting slots that goes into outside the scheduling window, they'll be fixed to 0 as well. So there's a lot of clever tricks we can do to reduce our search space and only look at so many variables being 1 or 0. And taking this concept even further, we can account for all recurrences, and the affecting slots for a given block can query for all the recurrences. So here, and it's really hard to show this in one screen, but for this 9:45 a.m. block, I can actually use the same logic to go and find what slots earlier in the week caused it to be occupied as well. So if linear algebra 1 was scheduled at 8 a.m. on Monday, and because it requires 3 recurrences, it's going to also occupy that Friday 8 a.m. Block, and thusly occupy the Friday 9:45 a.m. block too. So you can use this logic of slot occupation to handle recurrences too. And I'll show that in a second. So plug these variables, this grid of variables and feasible constraints into the optimizer, meaning you're not trying to schedule too much with only so much capacity, and then you'll get a solution. And most of the work will be finding the affecting slots for each block. Now, I did make a video earlier showing how to solve a Sudoku, and I would highly recommend watching that video, and I'll put the link in the description below. But the way you solve a Sudoku using a state space search is very similar, or is almost identical to how we solve the classroom scheduling. We just model our constraints differently. But here is just a brief recap of what I say in the Sudoku video. So if you have a Sudoku, hopefully it's a familiar concept. Every row, it's a number puzzle where every row, every column, and every square of 9 cells must have the numbers 1 through 9. And some of these values are already provided, but you need to find the rest. And so rather than do an exhaustive brute force search, think in terms of constraint programming to reduce the search space. The first thing you want to do is sort the cells by the count of possible values they have left. So as you can see, cell 44, it can only be, which is the very center cell, it can only be 5, because if you look at that row, that column, as well as that square of 9 cells it's in, the only value that is not being taken by any of those is 5. And this is pretty easy to create a function to find those possible values. And notice when we get to cell 1-4, there's 2 possible values, which are 2 and 5. And then at the very bottom, the cell with the highest number of candidates, cell 2-6, there are 6 possible values. And so this is known as a heuristic, where we sort where we have a priority of which cells we're going to solve first. Now, obviously, we want to solve the cells that are the most constrained and have the least possible values. And again, this is known as a heuristic. And then what we're going to do with this sorted list is we're going to create a recursive tree that explores each Sudoku cell and all of its possible values. And this is a state space search technique called branch and prune. And as you can see, from cell 4,4 all the way down to cell 1,4, there's only one possible value for each of those. So we just only explore one branch for all those, going 4,4 is 5, 2,6 is 7, 7,7 is 3, etc. When we get to cell 1,4, we then have two possible paths to take, one exploring it being 2, another one exploring it being 5. And so on the 2 branch, then we'll explore cell 0,7 being 3 or 2, and then cell 3 or 2, we'll explore it being a 3 or 2 again, because those are the possible values, etc. But notice when we explore on that very top first branch, we iterate through cell 4,2. When we evaluate it to be 3, that we can prune immediately, because if you look earlier down that branch, we've already evaluated that column 2 already has a 3. So therefore, there's no reason to explore a cell that puts another 3 in that column, because that breaks our Sudoku. And so we want to constrain and prune things aggressively so that we don't have unnecessary search space to go through. And then as soon as we have found a value for every one of the cells, then we have solved our Sudoku. And we have a branch of 81 nodes, each with a feasible value provided. So going back to the scheduling example, you could solve the scheduling problem from scratch with this very technique. Start with the most constrained slots first to narrow your search space. The heuristic I like to use are slots fixed to 0 first. Just get those out of the way because you know they're 0. And then followed by the Monday slots for 3 recurrence classes, because there's only 5 days in the week to schedule against. And 3 recurrence classes have to be Monday, Wednesday, Friday. That's the only way it'll fit. We should explore Monday for 3 recurrence classes being evaluated as 1 first. And something else you can do is proactively prune the tree as you go, eliminating any slots ahead that must be 0 due to a 1 decision propagating an occupied state. So that's a mouthful. And I'm going to go ahead and show how to implement this algorithm very briefly next. But if you want to schedule against multiple rooms, just plot your binary 1-0 variable against 3 dimensions, the slot, the class, as well as the room. But in this example, I'm going to just show how to do against 1 room. So I'm going to quit out of my presentation. And then I'm going to open up this application I built in Kotlin. So I have set up my scheduled classes right here, and that's my input. I also have the operating dates, and any week range of any dates will work. So you can see I have 2017 October 16th all the way to 2017 October 20th. So that is the week I'm planning against, and I think I just made it look at Monday through Friday. I just got rid of this Saturday, Sunday, not even bothering to explore it. And the operating day, it's going to be 8 a.m. to 17 o'clock, or 5 o'clock p.m. In the breaks, there's going to be 1 break from 11:30 to 1 o'clock, and I think I just ended at 12:59, so I allow things to be scheduled on the 1 p.m. And so there are my scheduled classes. And then right here is my main function. This is what kicks off the application. This should run pretty immediately. Obviously, I can throw really constrained cases at it, and it might test my heuristic and take a little bit longer. But this case right here seems to work just fine. And so I have this function called execute branching search. And if I go and jump to that, this is what does all the work. I have this class called branch node, which, for a given slot says whether it's going to be a 1 or a 0 on this tip of the branch. And this branch node can actually traverse backwards and look at all the previous nodes up to this point. And then we can use these previous nodes to figure out, have we broken our schedule yet? And should we prune this branch and abandon it and move on to the next one? I have a few other helper functions to, for instance, get the remaining slots that have not yet been explored on this branch, whether or not my schedule has been met still, or has been met yet, meaning that I've scheduled everything I need to. I also have these functions saying, is this branch continuable? Is everything still fine and I'm still good to keep traversing it? Whether this is actually a solution. And in this function, execute branch search, I already have slots identified which ones need to be fixed to 0, and I just fix them to 0. And I encourage, and then here I get I sort the slots by my heuristic, and I sort them by several things. So I sort them by day of week. So Monday is evaluated first because I'm going to try to schedule things as early as possible. And then I go through several cases. For instance, if there's 3 recurrences required, have those sorted first. If there's 2 recurrences required, then you only consider those slots from Monday through Wednesday, because once you get to Thursday, 2 recurrence classes won't even fit. And then I also have in my heuristic, the last thing it'll sort by is the number of slots needed per session. And then this traverse function, this is where the recursive call happens and it goes and explores the entire tree. And you can see here in this for loop, I'm exploring a value of 1 or 0 and creating a branch off of it, and checking if it's the solution, checking whether I need to continue this recursive search. And this function will keep calling itself until it finds a solution, if at all. And it'll come out null if no solution's found, and throw an error and just say infeasible. And then once I have the solution, which is going to be an entire branch with every node, I'm going to traverse backwards on it and apply the solution and set it to the variables. So let's go ahead and run this and see what happens. And there we go. So you can see here we have Linear Algebra 1 scheduled for Monday, Wednesday, Friday from 8 o'clock to 10 o'clock. English 101 Monday, Wednesday, Friday from 10 to 11:30. And you can see this ran pretty quickly. It ran in less than a second. And again, sometimes for many cases, you can be dealing with more combinations than there are observable atoms in the universe very quickly. So finding the right heuristic, finding the right search strategy to do the tree search is often critical. And unfortunately, there is not a one-size-fits-all for every single discrete problem. But for scheduling, for this particular scheduling problem, you might find a heuristic that works pretty well. So that is it. So that is how you can do scheduling problems and solving Sudokus using tree search. I hope you guys enjoyed this video. If you have any questions, please leave a comment, and also check out my written article on this subject on Torwood's Data Science. Thank you.